Oh, it's just like, oh, well, like, discover, screwed up, and get some like, so it's, I don't know, it feels strange.
Oh, your guys set up? I just thought that.
Yeah, well, like, we should go on that, right? Like, supposedly, like, you know, we simulated a human brain and we uploaded it to the car. Presumably you had some it's still not clear how to escape from there, right? It's like, right, so instead of running the 2D end, you can get the probability of reduction, so do that.
It's possible to do.
So I think we can start. Welcome to morning of Day3. The goal for this lecture is sort of to revisit something that was mentioned at the end of the first lecture on the first day by Dorit. So she introduced the EPR state, and then she told you, look, this state has some non-local properties. And she formulated this as using the game to generate the states to generate correlations in a game that was called the CHSH game. And there was a question also about that game, which was, well, what if you have more EPR pairs, can you play better in the game? So that's the question that we want to answer in this lecture. The answer is given by point 2 there, pros and from. Will tell us that we can't do more than that. But I want to use the lecture to say a little bit more, and not talk only about the CHSH game, but talk about the larger class of games. And what we get at the end is something interesting, which is that these games that we talk about, you know, we don't only talk about them in terms of, for purposes of verifying non-locality of quantum mechanics or doing things using entanglement that you can't do classically, but they can be used as building blocks to test certain operations that servers or provers or players are doing. And so you can use everything that I'm going to say today, but I mentioned that at the end, in order to achieve point 2 that I had in the lecture on delegation yesterday, which is delegating classical circuits to 2 quantum servers that share entanglement. The idea for achieving this are based on the things that I'm going to develop today. So let me sort of set up the model first. So what are these games? They're 2-player games. There could be more players, but I'm just going to concentrate on 2 players. And traditionally, we call these players Alice and Bob. And then there's a referee. Sometimes this referee is called verifier, so I try not to slip, but if I say verifier, I actually mean referee. Let's go in referee. And so how does the game go? The referee first selects questions. So there's going to be a question for Alice, I'm going to call it X, and a question for Bob, I'm going to call it Y. These questions are chosen according to some distribution of questions. So I'll give you examples. The question to Alice goes to Alice, the question to Bob goes to Bob. Each player sees their own question, and they have to give an answer. So everything is classical, by the way. We get quantum data. So don't try to find quantum states in this, it's all classical. So she replies with some answer, A, and Bob replies with an answer B. And then the referee is going to accept or reject the answers based on some criterion, and that's what defines the game. So the referee will check this criterion and write it B for verification. So there's a certain function that's computed, and if this function is equal to 1, then you accept. And if it's equal to 0, then you reject. Okay, so if the referee accepts, then we say that the players won the game, and if it rejects, we say that they lost. And so these players know the rules of the game, and they want to win. But the difficulty is that Alice only sees her own question, and Bob only sees his own question.
What is this?
What's this T? Oh my, I'm sorry. Yeah, thank you. X and Y. Yeah. I should not use S and T in the ball. So So the players are trying to maximize their chances of winning in the game, and they know what the rules are. The only thing that's making it hard for them is that Alice only knows her question and Bob only knows his question. So let me give you some examples that motivate also the study of these games. First, from just complexity, classical complexity theory, and cryptography, and then we get to quantum non-locality as the third example. So here's one motivation from complexity. It's, I'll give you an example of a game. I'm not going to analyze this game. It's in the exercises, but I want to just split it. We'll also get back to it tomorrow. It's called clause versus variable game. Okay? So this game is parameterized by a formula. So imagine that the referee has a formula, for example, the three-stat formula. So we saw these yesterday. It's a conjunction of disjunctions. So it looks something like this. Right? So we have an example. So for example, x1 or x2 or x3 bar. And then x4 or x1 bar or x2 and etc. Right? So that's a formula. Everyone knows what the formula is. It's a formula on a certain number of variables, and we'd like to decide whether this formula is satisfiable. So does there exist an assignment to the variables that satisfies the formula? And we're the referee, we don't know that, and we're going to play a game with the players such that if the formula is satisfiable, the players can win, and if it's not, they cannot. So what's the game like? What the referee does is he chooses the clause is C, let's call it C. So for example, the second clause, so let's say C equals x4 or x1 bar or x2 at random. And then Alice's question, in my notation is a bit, there's too many x's, right? So, okay, so Alice's question is going to be the three variables in the clause. So just x4, x1 is the list of the labels, x2. And Bob's question is going to be one of the variables chosen at random. Right? So for example, x2. Okay? So I chose a clause, and I'm sending to Alice these three variables and to Bob just that one variable. So what am I asking them to do? Right? So what do they need to do in order to win in the game? So Alice's answer, I want it to be 3 bits. So maybe let's call them A prime, A double prime in 0, 1. And Bob's answer, I want it to be 1 bit, B 0, 1. Okay? So Alice got 3 variables, she has to give me 3 bits. Bob got me 1 variable, he has to give me 1 bit. And what I'm going to check that this satisfies the clause and that they're consistent with each other. Right? So the referee, I put it up here, the referee's check is going to be that A prime, A double prime satisfy the clause C. So not the whole formula, right? Just this particular clause. So for example, if the clause was this, what should it be? For example, if all the A's are 0, this is fine, right? Because then I read 0 here, I negate, I read 1, and then 0, so that's good. Okay, so 0, 0, 0, that's a valid answer for Alice. This is one that's wrong. The one that's wrong would be if she tells me 0, 1, 0. Because then when I negate the 1, I get 0, 0, 0, and the clause is not satisfied. Okay. So 0, 1, 0, they're out, but anything else, Alice is fine. That's one check. And then the other check is that Bob is consistent with Alice. So Bob is consistent, meaning that with Alice, meaning that this B there is supposed to be the value, an assignment to the variable x2. Alice, I also asked about x2, right? And for x2, she told me A double prime. So I'm going to check that B is equal to A double prime. So in that particular example, if they just send me all zeros, it's going to work out, right? Because Alice says all zeros, it satisfies the clause. Bob said a 0, it matches that's fine. Something that wouldn't work is Alice says 0, 0, 0, and Bob says 1. Then I'm going to reject. Because Alice is telling me, well, I think that x2 should be 0, and Bob is telling me, oh, I think that x2 should be 1, and that, that's suspicious, so I don't have anything to use. Okay. So the claim that I'm not going to prove, maybe I can just explain. So the claim is that the formula is satisfiable if and only if there exists what's called a perfect strategy, so a strategy that wins all the time, whatever the verifiers, the referee's random choices are.
sorry, again, I missed this point, but does the referee send the clause to the players, or is that?
He sends the variables of the clause, so it kind of leaks the clause, right? He doesn't say if it was negated or not, but the players do know the formula, so they kind of look it up. So if you want, you can think that Alice gets the clause. What's important is that Bob gets much less information. Bob only gets one variable, and he doesn't know which clause I took it from. So that's important. Otherwise it would be easy for them. Right? So that's the point, right? They don't know each other's question. And Alice, she knows that Bob gets asked one of these variables, but which one? She doesn't. So she has to be very careful if she starts lying about something. Yeah.
If it's just one clause, can't they always get every added to be one? It's always consistent.
Yeah, so the formula has many clauses, and the referee chooses one clause at random, and he sends it to Alice. But to Bob, he only gives the variable, not the clause. Okay, so they have to be very careful.
He doesn't know from which clause.
He doesn't know from which clause, that's the truth. Yeah. So one thing that's should be easy to see, that everyone can see, is that if the formula is satisfiable, then you can win in this game. Okay, how? You just figure out what's a satisfying assignment. These players, they have as much time as they want. You find a satisfying assignment, and then Alice and Bob just say, look, we're going to use the same satisfying assignment, both of us, and that will work, right? And so whenever Alice is asked three variables, she just sends the values in the satisfying assignment. It's a satisfying assignment, it satisfies all clauses, so it's going to check. Bob says the same thing as her, so it's going to check also. Okay? So if the formula is satisfiable, they always win. What's a bit more tricky is that if they can win, for sure, then the formula is satisfiable. That's not completely obvious, right? Because it doesn't look like, as you were pointing out, in the game I only choose one clause, but I choose it at random. So if you want to win in this game of quality 1, you need to have, you need to be ready for every possible clause. So Alice needs to have something that she's going to answer, whatever the clause. But it can depend on her, because she gets to see the clause. But then Bob cannot depend on the clause. And so that's not a super important game for today's lecture. It'll be more important tomorrow, and I put it in the exercises so you can think about the reverse direction. What's more important is that you understand that this is a game, and you can see what it looks like. But it's one motivation for studying these games for complexity theory, because as a consequence, if you believe this, and you know that the 3-stat problem is NP hard, then you immediately have as a corollary that given the description of the game, how hard is it to determine if there exists a perfectly winning strategy for the players in the game? That's NP hard. Because if you could do that, then you could take that particular game, figure out whether there exists a perfect winning strategy for the player or not, and then we tell you the formula is satisfied. And that's hard. Okay. So even given such a simple game, it's pretty hard to determine if there's a perfect winning strategy. So that's my motivation for complexity. There is also a motivation from cryptography for studying the games. And there I'm not going to even give you the game, because the games there tend to be a little bit more complicated, but they arise when you study protocols, interactive protocols in cryptography. In particular, there's a nice game that's called the commitment game, where the players play with the referee, and the outcome of the game is that Alice commits to a bit, Bob reveals the bit. So these games, they were introduced, for those of you who know, in studying zero knowledge, so trying to get interactive proofs for languages in NP that have perfect statistical zero knowledge, then these games come in. So if you don't understand these words, it doesn't matter, it's just anyone is interested in this. The motivation, third motivation is one that preoccupies us today, is quantum foundations, or study of non-locality. And so a typical game, the most important game in that area is the CHS8 game that Dorit mentioned on Monday. And so let me give it to you again, so that we have a second example of a game. So this one is much simpler. So the questions to Alice and Bob, they're just bits. And the answers, they're also bits. And then the question is when our answer is valid. And so here's the criterion. The answers A and B are going to be valid to the questions X and Y, if and only if. So let's say equals 1. If and only if the parity of the answers is equal to the AND of the inputs. It's kind of a strange condition. Maybe it's useful to list it as a table. I'm going to try to draw the table here. So the inputs X and Y can be 0 or 1, and then the outputs, I'll write here what the parity should be. Okay? if the, okay, I'm not going to, let's draw the table, take enough space. A and B. Okay, so the inputs, they could be the questions to these players, that's the four possible possibilities, right? And this is saying that I'm going to write what are the valid answers here, and it's like this. Okay, because the and of the inputs is 1 on the last row, and then the other one's 0. Okay. So the goal for these players is to come up with A and B such that the parity of A and B most of the time is 0, but in the last case is 1. So this is saying that they have to give me the same answer, different answers. So the question is, I haven't fully specified again because I haven't told you how I choose the questions. There's a distribution of the questions. But this game is just a uniform distribution. So the probability that I choose a question x, y, which is this pi that I have over there, is a quarter for each x and y. And so the question is, what is the maximum success probability of players in the game? So what's, yeah.
Are Alice and Bob supposed to be aware of the distribution pi?
Yeah. So Alice and Bob know everything in terms of what's the description of the game. What they just don't know is once the game starts, then you only get to see your question. So everything that I wrote on the board is public. But then when the game actually starts, Alice is there, Bob is there, and they get questions 0 and 1, and they have to figure out an answer. But they can decide beforehand. They can say something like, look, Bob, I'm just telling you, here's what I'm going to do, right? If I get a 0, I say blah. If I get a 1, I say blah. And Bob says, etc. The only thing is that when you get your question, you don't know Bob's. So, okay, so what's the best? Can you win in this game? And if not, what's the best that you can do?
75%, you just always choose the option of just anyone else is going to be it.
Yeah, that's an example of a strategy. I just always answer 1. Is that what you said, or no?
Other way around, they always answer differently.
Oh, then that's not going to do so well because they always answer differently. So
Yeah, sure, the same.
always the same, right? So they just decide to always answer 1. Well, it's kind of a stupid strategy, but half the time they get it right still, right? Sorry, 3/4 of the time they get it right, just because that's how my game is set up, right? We're kind of stupid, so can you do any better? Okay, so exercise you cannot, we're going to prove this a little bit later, but if you're bored, you can just prove that. And you could just exhaustively search, right? But that's the best that you can do. And the reason that we're studying this game is that if I allow a slightly broader set of strategies for the players, so same game, I'm not going to change the rules. The only thing is that I say is that, well, what if now Alice and Bob, we didn't kind of discuss how they computed A and B, right? We just said, well, they only see their question, they have to compute A and B. What if before the game started, they created some state psi, for example, the EPR state in a corner, and then Alice got qubit 1, Bob got qubit 2, and then they left, they got separated. And then when Alice gets her question X, she maybe makes a measurement on her qubit and she gets an outcome, and she uses that outcome to determine the answer A. So that doesn't seem to violate the rules of how I described the game. It's still, there's no communication. Alice is making a measurement on her qubit, Bob is making a measurement on his qubit. They don't talk to each other. This entanglement state is prepared beforehand. But the point that we see that later is that using this EPR state, you can actually win in this game with probably better than 3/4, 85%. It's kind of surprising because if you come up in your head with a proof that you can't win in this game with probably 3/4, then you're confused, right? Because you prove it. The reason is that your proof makes some assumptions, and so you get it. So that's the plan, that's the goal for today. I'm first going to give you a slightly more general model of quantum games that are called quantum XOR games. And we discuss what classical strategies for the players look like in those games, what quantum strategies for the players look like in those games. And then we'll apply that to the CHSH game, and we prove everything that I said. So that the best classical is 3/4, that you can do 85% quantumly, that 85% is also the best that you can do quantumly. And then later, we even go further and argue that not only 85% is the best that you can do quantumly, but there's the only way you can do it. And the only way that you can do it is the way that I'm going to
Are there known complexity theoretic implications of the perfect strategy?
There are. I'll say a few words about complexity theory. Not, yes. Depending how you refine your statement. Because you can define complexity classes based on, like it's like what I mentioned, right? So from this game, we had the property that computing the best winning strategy of such a game is NP hard. The fact that using entanglement you can sometimes do better implies that this theorem or this claim here is false if I allow the players to use quantum strategies. And so that means that breaks this NP hardness statement, and we have to do other things. So it's something that we'll talk about more tomorrow. So yeah.
I'm just curious, is there a 3-bit game that you can win 100%?
The what, sorry?
Is there a 3-bit game that you can win 100%?
What's a 3-bit game?
A similar game, but maybe 3 inputs. Because I'm thinking this has to do a lot with Bell's inequality, but then there's like the GHCM experiment. That,
So then in that case you meant a 3-player game.
3-player? Oh, okay.
Yeah, so GHC is a 3-player game. I'm not going to discuss it, but
yeah.
it's a 3-player
Yeah, 3-bit
game.
and 3-player.
Yeah, so the answer to your question is yes. So
Okay.
this CHSH game is a game such that the classical players can do 3/4, the quantum players can do 85%, and his question is there some other kind of game where we could have something even more surprising, right? Where the classical players, maybe again, they can do 3/4, but the quantum players can follow them. The answer is yes, you can achieve this by using either a 3-player game, the GHC game that I'm not going to discuss. You can also do it using 2 players. There's a fun game called the Magic Square game. Maybe I'll say it later because it's a fun game. And that game is one that you can't win. I'll say maybe tomorrow because it's an example of this kind of game where the classical players cannot win, but the quantum they can win using 2 EPR. So these things happen. But not for XOR games. That's the class that I'm going to discuss today. And CHSH is an XOR. Other questions? Okay. So ready? We're going to describe the model. So there are going to be games of this form. So let's see. I'm going to do this. Okay. So what's a XOR game? It's just same kind as this, but it's more restricted. So I put special restriction. The special restriction is that this decision to accept or reject should be a decision of the form that we have over there in the CHSH game, meaning that it only depends on the parity of the input. So XOR game, maybe I'm going to erase this. Okay. So XOR games are going to be like this. We have a distribution on questions, so that didn't change. But then the decision to accept or reject is, so I'm going to write, okay, so for notational convenience, I'm going to index these questions, I'm going to write these questions as integers, okay? So the question to Alice, x, is just going to be an integer between 1 and n. And the question to Bob, y, is going to be an integer between 1 and m. Okay, n could be equal to m, or it could be different. For example, of CHSH game, n and m is 2, right? There's 2 questions to each of them. And then there's a distribution by, which gives me the probability for a pair of questions I and j. And then the special case about XOR games is when do I decide to accept or reject the answers. So there's going to be just a little coefficient. I'm going to call it c, Cij. I'm sorry. I haven't told you what the answers are. The answers A is going to be just a value that's -1 or 1. Instead of 0, 1, it's convenient to have the answers being -1 and 1, A and B. Okay? So the answers, they always have to look like this. And then when do I accept an answer? So there's a coefficient Cij that depends on the questions. So the questions, they look like I and J instead of X and Y. Sorry. Change my notation. Cij is in -1, 1. And you're going to accept if and only if the product of the answers is equal to the Cij. Okay? So AI, the answer to question I, times Bj, the answer to question J, is equal to Cij. So, example, I can reformulate CHSH in this form, so maybe it's useful to do it. So, example, CHSH.
There's something I don't understand. So
Yeah.
when you write AI and BJ, so you assume that they decided in advance what the answer is going to be for question I and question J.
Sorry, I imagine what?
So when you write AI and BJ, so do you mean that they somehow decided in advance what the answers are going to be for question I?
No, it's the check. So in the game, the referee chooses questions I and J. He sends I to Alice, and Alice has to reply with bit AI.
Right. But you do not mean that AI depends just on I, right?
Yeah, I do mean that.
But
Because
then,
Alice only
but
gets to see I.
if they use entanglement and somehow.
Couldn't they have
Distribution. Yeah, so I'm describing classical strategies here. But no, so the point is that whatever they do, sorry, it's a good point, but this is fine. Whatever they do in the game, they can use entanglement, they can use shared randomness. In the end, I ask them a question, they reply a bit, and you're right. I write Alice's answer in question I as AI. This can be a random variable. It can be correlated with BJ, but I just call it AI. Alice's answer in question I. But you're right, when we get to entanglement, these two random variables are going to be correlated, and we'll have to understand what distribution can you get using entanglement and how that plays into the success problem. Thanks.
Was another question?
Oh, I was going to do the example for CHSH. So the distribution is just a quarter, a quarter, a quarter. And what are the C coefficients? So just if I do the translation, then I get that C11 equals C12 equals C21 equals 1, and C22 equals minus 1, right? This would be if I just change my game. Instead of looking at the parity of A and B, I look at A and B not as bits, but as values in minus 1, 1, and I take their product, right? So it would be A times B, and then I would ask the product of A times B to be 1, 1, 1, minus 1. And then this strategy is to run forward. So it's just a change of notation, but it's easier to write things. So is there okay? Questions on the how I define the game? Yeah.
I'm confused about the answers here. Why shouldn't there be more minus ones? Because there's more.
Minus ones here.
Sorry, I'm probably looking at it wrong.
Okay. So now it's the product, right? And so A and B are numbers are 1 or minus 1, and so I want them to be equal. So it means that their product is equal to 1, and that's what I'm writing here: equal, 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 different.
I'm just confused about why they want to be equal now, because before it had something to do with the, it still has to do with the
No,
X,
because-
Y, and still has to do with the,
Yeah. So before it was the case, right? That in this row, the answers had to be equal, 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 and different. That was the rules of the game: equal, 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 different. And that's exactly what's written, right? So the product equal to 1 means that they should be equal, 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 different. Maybe I should have done that from the start. So now we're just looking at answers minus 1 to 1, and it's that the product should be equal to minus 1 of the answers. Change the notation. Okay, so this is the specification of the next game. I'm going to write an expression for what is the maximum success probability of classical strategies first, and then we talk about quantum strategies. But we have to go slowly over classical strategies before we can understand the quantum ones. And by classical strategies, I'm going to be really the simplest thing, which is that these players get a question I and they reply with AI, right? So this is the setting that Shahar was saying, well, what if, etc. No, so now I'm just, the strategy is Alice needs to assign a value to each possible question she can be asked, and Bob needs to assign a value for an answer to each possible question he can be asked, and that's their strategy. And so the maximum success probability of a strategy in the game, I'm going to call it the value of the game. So the maximum success probability is kind of an important expression, so I'm going to write it. So it's going to be the supremum over all strategies, and the classical strategy, as we were saying, is just an assignment of answers. So it's values AI and BJ in minus 1, 1. of what? So once I fix the strategy, what's the probability with which I win in the game? Well, what happens in the game is that I sum over all questions. There's a certain probability that I ask the question. Okay. And then I need to multiply this by 1. I win if the answers are valid to the question. If the answers are valid to the question, let me write it. Okay. So I claim that this is the maximum success probability of players in the game. So can we see it or not? I mean, it's a maximum over strategies, right? So when I write AIBJ, I mean A1, A2, A3, AN, and B1, B2, B3, BN. So this is whatever Alice is going to say and whatever Bob is going to say. So I'm taking the supreme over these. And then I'm taking this is like an expectation over the questions, right? So sum over all possible questions, or the probability of asking the question. And what is this? This is 1 if they're correct and 0 if they're wrong. Okay? If they're correct, I wrote it here. AI bj equals Cij. If I just, these are plus minus 1 numbers, so it's the same thing as saying that this is equal to 1. So I get 1 plus 1, 2 by 2, I get 1. So if this is satisfied, I get 1. If it's not satisfied, then this is going to be minus 1, so I get 1 minus 1, 0, divided by 0, so I get 0. Right? So this expression is 1 if you get the right value and minus 1 if you. The reason I'm writing it this way is that it's convenient to expand this product here. And I'm going to get, by expanding it, I'm going to get a half plus a half sum over ij of phi ij, c ij, ai dj, and I forgot the supreme here. I just expanded the addition, and then the first part just has a sum of the probabilities divided by 2. This is a distribution, the sum of the probabilities is 1, so I just get 1 by 2, and then that I just copied the other half here. So that's the quantity we're going to be staring at for the remainder of the lecture, so it's going to be important to parse it. I'm going to parse it on the example of the, we're going to apply this to the example of the CHSH game. Yeah.
So they're not allowed to use random coins? We're looking at pure
Yeah, that's a very good question. They are. I'm simplifying a little bit here, but they are allowed to use shared randomness. If they use shared randomness, then we get into the regime that Shahar pointed out. So this AI and BJ are random variables that depend on the shared randomness. And so in that case, it's an important point. In that case, what I have to write is these are not just bits in -1, 1, but they're functions of the shared randomness or random variables. And so here, I would have to write what's the probability that you're correct. And so this was 1 if you're correct and 0 if you weren't. And so I'd have to write an expectation here over the shared randomness. Let's call it capital R. And so this expectation here, this is just a half, it's going to stay a half. These are constants, but here I would have an expectation over the shared randomness of the product of their outcomes as random variables for the shared randomness. This is important because this is how we're going to write the quantum case, so it's a good question, thanks. In that case, though, it doesn't matter, because when I'm interested in the supremum, it's not going to be an advantage to use shared randomness, because when you use shared randomness, your success probability is going to be the average over all possible shared random strings of how well you do if that's the random string. Okay? But then if on average over distribution on random strings you do a certain way, then why don't you just choose the best random string, right? Because you can figure that out beforehand, you can do the addition. And so you can just fix the best random string, and it actually wasn't useful for you to use shared randomness. Okay. So basket players are allowed to use shared randomness, but it's not helpful for this kind of thing. All right, so let's prove our first theorem, which is that classical strategies in the CHSH game cannot do better than the strategy that was pointed out earlier, which is 3/4, right? I mean, there's many ways to see this. I'm doing it in a more elaborate way than needed, but it's going to be useful later on. So I'm going to give a name to this quantity here. no. I'm going to call it the bias of the game, beta. I use beta for the notation. And so this maximum success probability, omega, how well you can do is always going to be half plus half that one. Writing in this way represents the fact that in a game of this form, in the next door game, you can always win the probability half. That's easy, you just reply random answers, and if you apply random answers, then there's always going to be probability half that you satisfy this criteria, whatever the C is. So you can always win probability half. What's interesting is how much better than half can you do, and so that's what this quantity is telling us. So that's what I'm Okay, so in order to bound the success probability that players can have in the CHSH game, we need to bound this, right? So I'm going to write it for the CHSH game. So CHSH game, oops. I just write the exact same thing, but for that particular game. So half supremum. So CHSH game, there's only two questions. So we just have A1, A2, and B1, B2. Okay. And then I have the sum over all questions, but each question has probably a quarter. And then what I need to write at every step is the coefficient C times the answer A times the answer B. And these coefficients C, I just erase them, but they were 1, 1, 1, minus 1. And so what I'm going to get is, let's write it as A0, A1, B0, B1.
The 1/2 is inside the bias or outside the bias?
Just
fixed notation.
Yeah, no, you're right. Yeah, thank you. So I'm going to get A0, B0 plus A0, B1 plus A1, B0 minus A1, B1. Okay? That's the maximum bias that we can achieve in the CHSH game. It just represents the fact that to win with probability 1, what do you need to do? If the questions were both 0, you need to get the same sign. You get 1 here. If the questions were 0, 1, you need to get the same sign. You need to get 1. You need to get 1. And the last time you need to get minus 1. If you get minus 1, then with the minus you get plus 1, right? So you get 1 plus 1 plus 1 plus 1, 4, divided by 4, 1. If the bias is 1, the value is also 1. Okay. So if it's possible for you to find 4 plus minus 1 numbers, such that this is 1, 1, 1, and this is minus 1, meaning exactly what it is to win the CHSH game, then you win the probability 1. And so what you want to do is that you count. So there's many ways to do this proof, but let me give you a way that's going to be useful later on, which is to rewrite this expression. How do you see that this cannot be? I can rewrite it in the following way. A0 times, just factor it, plus B1, plus A1, B0 minus B1. Okay? I just factored it in. And so this supremum is going to be less than the supremum over B0 and B1. What's the best choice? This is a certain number. A0 has to be a sign, plus or minus 1. The best thing that I can choose for A0 as a function of B0 and B1 is whatever sign they are, so I get the absolute value. So I can write it in this way, plus B1, plus B0 minus B1, divided by 4. I just said these, I took an absolute value here, and the absolute value of A0 is 1, and this absolute value is whatever it is. The absolute value of A1 is 1, and the absolute value is okay, well, what's the maximum you can do? I mean, now we're pretty down to not so many options, right? And I mean, whatever I do, I can make one of these quantities 2, but then the other has to be 0, right? I mean, either these guys are the same, and so I get 2 and 0, or they're different, and I get 0 and 2. But I can't do better than that. So this is at most so as a consequence, we have shown the following theorem, which is that the classical value of the CHSH game is at most 3/4, right? Why 3/4? Because it's a half plus a half times the bias, and the bias will be bounded by half, so half is 3/4. Okay, so that's what we found earlier was the best that you can do. This is okay? The goal now is going to be to do the exact same thing for quantum strategies. So it's going to get a little bit more complicated, but not too much complicated. And we're going to try to do the exact same computation, but what if it's a quantum strategy? And we'll see, do we get the same bound or do we not get the same bound? To succeed in doing that, we have to, so I think I'm going to erase this because I need the space. I have to formalize quantum strategy. So what's a quantum strategy? There's going to be three things. The classical strategy was just, whatever Alice does and whatever Bob does. And so it's just a list of answers for Alice and a list of answers for Bob. Maybe they could use shared randomness, but I was not research. Quantum strategy has one more element, which is what is the quantum state that they share. Okay. So how you specify a quantum strategy is you have to specify three things. One is you have to specify a state psi. And this state psi is going to be a state that's on Alice and Bob. And the way I write it is this way, page 8 and 8b. This is Alice's qubits and Bob's qubits. Right? So for example, it could be C2 tensor C2. And it could be the EPR state, that's just a 2-qubit state, and that's Alice's qubit, A, and that's Bob's qubit, B. But they don't need to have just one qubit, right? They could have a qubit, or they could have like 5 qubits, or they could have whatever number of qubits they want, each of them. But the state has one part for Alice and one part for Bob, right? And Alice only gets her part, Bob only gets his part, right? That's the requirement that these guys don't talk to in the game. They each have their own system, but they can choose the state beforehand. So that's the state, and then the second thing that I have to, we have to specify is, okay, what do they do in order to determine their answers? Well, they have their states, they make a measurement. So I have to specify Alice's measurements. On each question, right? So on question I, when she gets the question, she makes a measurement, I have to specify Bob's measurement. And so what are these measurements supposed to return? An answer in the game, so +1 or -1. Right? And we've seen that measurements that have outcomes +1 or -1, we can represent them using observables. So just remission matrices that have these eigenvalues, +1 and -1, that represent Alice's measurement and Bob's measurement. So Alice's measurement in question I, this is just going to be an observable AI. So just to remind you, an observable is a remission matrix, or remission matrix, remission with eigenvalues ±1, right? For example, the X matrix or the Z matrix, that's fine. And then Bob's measurement on question J. This is an observable BJ. It also has eigenvalues +or -1. Okay. And so that's enough, that's it. That's a complete specification of the strategy. Now I know exactly what these guys are doing. They start off the game sharing this state psi. Alice has the A part, the first few qubits. Bob has the B part, the remaining qubits. Now the game starts. Alice gets to question I. Bob gets to question J. What do? They make a measurement on their state. What is the measurement? The measurement is specified by this observable AI. So this observable has a +1 eigenspace, or -1 eigenspace. You make the measurement in these two eigenspaces. You're going to get an answer, +1 or -1, and then you return that. The same for Bob. So now, yeah.
Does it require proof that this is the most general quantum strategy possible?
It sort of does. So in the sense that, but I don't know what else you could, we haven't really defined the most general kind of measurements you could make. So you could sort of argue a little bit. But that, one thing that might be confusing is you might be thinking, well, she makes a measurement, but then why does she have to use that outcome, right? Why doesn't she think a little bit longer, make another measurement, go for a walk, etc. But you can put everything in the specification of the measurement. So it is a fact that it's the most general, but to sort of prove that, you'd have to say, well, what are the laws of quantum mechanics and what can you do from it? So it would take like a semester to get there or something. But it is the most general. Yeah.
I have a question. So in the classical game, right, they can keep playing the game again and depending more resources. But here somehow I want to make an observation, they kill their state.
That's true, but I allow them to start off the game with many copies of the state if they want.
But then let's say they start with many, but they want to play many more rounds, right? So somehow I give you some initial information, and then they want to play for infinitely many rounds.
Okay.
So can they actually use quantum power to do something?
No. So for example, that's a harder theorem to prove. But it's a theorem that if you play the game CHSH
sort of infinitely many times, but I allow you to use quantum strategies, but I limit you to only 100 qubits. That's what you have to start with, right? And then let's see how well you can do. If I play the game 1,000 times instead of 100 times, then you're not going to do it. So you can prove the theorem that every time, in order to succeed in the CHSH game, every time you succeed, you need to burn some autonomy. And so if you start with a finite number, you're going to run out.
Is this just for the CHSH game or for any game?
You want to say that it converges to the classical value, Shapa?
What?
You want to say that it converges to the classical value? Like
I'm asking.
If you bound the amount of entanglement.
I'm not saying anything, I'm asking.
Yeah,
Does it converge to the classical bound?
I think it is the case. Yeah, I think it is the case. If you bound the number of qubits.
Isn't it like just if you have a measurement, you consider subspace. So every time you make a measurement, you're going down in your dimensions. So you cannot repeat this strategy too many times. So at some point you reach the situation when you don't have any quantum state. You have classical state.
It's the right intuition, but it's a bit harder to do.
I mean, unless somehow your observations or sort of aligns will not really collapse the state. I mean, somehow you make it so that
any observation collapses you to the to the subspace anyway. So you cannot do this.
I mean, there are examples. Maybe
let's table this because you have the right intuition, but you don't have the proof. So if you try to actually, it's a bit. I think both of you are right because that's what's going to happen. But it's a bit tricky to show that you do need to destroy some amount of atoms. Jar is right in the sense that if the outcome is kind of predetermined, if you're pretty sure what outcome you're going to get, then the state, the state is like this, and you make a measurement where it just moves like a tiny bit because then you're really not affecting it that much. And so, but the point is that if you didn't affect it that much, then it's not being helpful to you either. You could have done that classically, and so. So that's our strategies, and we need to see how well it does, right? So to see how well it does, I'll rewrite what I had there, and it's the same thing, right? So I have the value is a half plus a half the bias. This is going to be the same, but now I'm going to put stars. Star refers to the quantum values, okay? Stars and entanglement. And so how well can you do with entanglement? Well, it's the supremum. And I'm going to write the same expression as we had before first. So it's going to be the supremum now over all possible strategies, right? So all possible states, whatever dimension, all possible measurements for Alice, all possible measurements for Bob, of the sum over ij, pi ij. I have this thing, which is just a coefficient of the game, right? 1 or minus 1. And then in the classical case, we had ai bj. Okay, that was just the product of the answers. Now these answers are not fixed, they're the outcome of a measurement. The first modification that we saw earlier is that we said, what if they have randomized strategies? Well, if they have randomized strategies, what should go is not the product of their answers, it's the expectation of the product of their answers because you choose the randomness. So in the randomized case, we have this, where these are functions of R, right? So AI of R, bj of R. So now in the quantum case, what I have to write is the exact same thing, but I have to write what is the expectation of the product of the outcomes of making these two measurements, AI and bj, on the entangled state side. So we know the rule for this, right? So just as a side comment, if I have an observable from x, so it has plus minus 1 eigenvalues, and I make a measurement on the state side, I'm going to get outcomes 1 or minus 1. And what's the expectation value of the outcome that I get? It's this, right? Is that okay? So this is the expectation value of the outcome of performing the measurement specified by the observable x on the state side.
Is the dimension of psi fixed beforehand? Or?
No. So that's a good point. So one way to write it is I could put an integer d here, and then psi would be a d by d dimensional state. It's not fixed beforehand. So that's why in the classical case it was not important that I wrote supremum to be maximum. In this case it is important that I write supremum because okay, so this is the rule for the expectation value of a single measurement on an entangled state side. And so the same rule for making two measurements, AI and bj, is going to say that I have to replace this expression by psi AI tensor bj psi. Okay? Alice is making her observable on her side, Bob on this side. So the product of their outcomes is going to be given by the tensor product of these two observables if I measure in the state side. And so this is really the expectation of the product of Alice's outcome when she makes the measurement times Bob's outcome. So I have to write this expression. And that's it. It's just a very simple generalization of the measurement rule for Alice and Bob. And that's it. That's the formula. And now we need to say things about it. Okay, so is that okay? Questions on the and so now the question is, how large is this expression for the case of the CHS game? So there's two things that I want to show. One is verify the Reed's claim from one day that you can make this number equal to something bigger than half, right? In the classical case, we have half here. I want to show you exactly how to make it bigger than half. We do the calculation. And then I will also show you how to bound it, how to say that you can't do better than 1. Yeah.
You can also just write it as like the trace of like AI tensor Vj times the density matrix, right?
Yes.
You also generalize the randomized, like classical distribution case.
Yeah, you can, that's true. If it's helpful to someone, you can write this as using the usual cyclicity of the trace thing that we did a few times yesterday. It's okay to write this in this way, right? Because cyclicity will say the bra there would come over there, and I get this. And I can allow a density matrix if I want. That's not going to help for the same reasons that the shared matrix because density matrices are complex combinations. But you're right, that's another valid way to write it. So now I'm going to give you a strategy and see how well it does. Okay? So it's going to be a strategy for the CHS game. So I need to specify the state and the observables. So what's the state? For convenience, I'm not going to use exactly the EPR state that Reed had, but something equivalent to it. I'll write it in this way. So 1 by root 2, 0, 0, plus 1, 1. Okay? The EPR state has 0, 1, minus 1, 0, but we also saw that they're equivalent if you just apply an X on the first qubit and a Z on the second qubit. And anyways, I get to choose the state I want to choose, so I'm choosing this state. Okay, so that's the state for Alice and Bob. I have to say what are Alice's observables. So Alice's observables are simple. For the question 0 in the CHS game, I'm going to choose an X. And for the question 1, I'm going to choose a Z. So very nice observables for Alice. Bob, they're a little bit more complicated. For his first observable, I'm going to choose the Hadamard. So we've used to thinking of the Hadamard as a gate, but it's also an observable, right? As plus minus 1 eigenvalue, just for extra identity, that's fine. And then for the V1, I'm going to choose what's sometimes called the G. It's the conjugate of the Hadamard by Z. I'm just going to tell you what the matrix is. So it's 1 by root 2, 1 minus 1, minus 1, minus 1. Alright, now we just have to do the calculation, right? So we plug this stuff in there, and we see how well it does. So we have to compute 4 expectation values, right? When Alice gets question 0 and Bob question 0, 0, 1, 0. So I'm going to give you a little trick that's useful in general and that lets us simplify the calculation. So what we have to compute are things like, this is what we have to compute, right? A tensor B, psi for this side. I have to compute this in 4 cases where this is A0 or A1, B0 and B1, right? And that's all the expectation values. So let's just expand it out, the cross product. And so what I get is I get 0, 0, AB, 1, 1. I'm a little sloppy, I'm not writing the tensor product, but it's shorter this way. So plus the cross terms, so AB, 1, 1, plus 1, 1, AB, 0, 0, plus 1, 1, AB, 1, 1, and I forgot the 1 by root 2's that become a half a drop, right? So this is just AB can be anything. I just use the definition of psi like this and just like expand the whole thing, right? And so I get this expression. Okay? Now this is, I can split this out. This is a tensor product. So the first 0 and the first 0 go to A, and the first 0 and the first 0 go to B. And so I can rewrite this expression as 0, A, 0, 0, B, 0, plus 0, A, 1, 0, B, 1, plus the other terms, right? There's 2 other terms. Why am I writing this? Because this is equal to half the trace of A times B transpose. you can think of this as an inner product between the two matrices. That's a nice fact. I mean, it's a linear algebra fact, right? If I take any two matrices and I evaluate the expectation value on this state there, this psi state, then it simplifies down to just the half times the trace of A, B transpose, which you can think of as an inner product. So why did I get that? Because see, what is this? This is the upper left entry of A times the upper left entry of B. That's the upper right entry of A times the upper right entry of B. And then I have the bottom left, and bottom right, right? So I'm just taking a half times like the product of the entries of A and B that match, and that's the expression. It's not too important, except that it's allowing me now to do the calculation very easily here. So if we compute what I really wanted to compute, it's psi AI tensor dj psi. This is the important part, what is the expectation of the product of the outcomes that are returned by this quantum strategy for each possible pair of answers? Okay, and so we have to do it. So let's see if you know your quantum matrix as well. For A0 and B0, what am I going to get? So I have an X and I have a Hadamard. Maybe I should let me spell out the Hadamard for you so it'll be easier to see. B0 is 1 by root 2, 1, 1 minus 1. Okay. And so I want to compute this expression here when A0 is X and B0 is the Hadamard. And the way to do it is I just described to you, you put a factor half in front, and then you just take the entry-wise product of the entries of the matrices and you sum it up. Okay. So the X matrix is like 0, 1, 1, 0. So for the diagonal coefficients, I'm going to get 0, but then for these, I get 1 times 1 plus 1 times 1. So I get 2, divided by square root 2, divided by 2 there. So I claim that for the 0, 0 case, I get 1 by root 2. Maybe let's do another case. Let's do A1 and B0. So I have a Z, right? The Z is like 1 and minus 1. So these don't count. But 1 times 1 plus minus 1 times minus 1 gives me 2. By root 2 by 2, same thing. Okay? We can do X and B1. Did I get it wrong? I got it wrong. So I need to invert these two. Sorry, it's okay. Okay. Let's continue. So let's do A0 and B1. So this is Z, right? So I get 1 plus 1. So again, I get 2 by root 2 by 2 is the same thing, right? All the same thing so far. Except now if I do these two, X looks at the off-diagonal term, so I get minus 1, minus 1. So I get 1 by root 2 for the cases 0, 0, 0, 1, and 1, 0. But then for the case 1, 1, the expectation value of the product is minus 1 by root 2. So this is nice. You can see these guys are doing exactly what they're supposed to do, right? If the questions are these three cases, the expectation of the product of their outcomes is not 1, I would have hoped 1, but it's 1 by root 2, which is root 2 by 2, which is 0.7. So it's pretty close to 1. And if the two questions are 1, then bam, they get the minus. So they're also in the right direction. And so we can compute, maybe just here, how well they do for this bias. So I'm going to get a quarter times 1 by root 2 for the first, plus 1 by root 2 for the second, plus 1 by root 2 for the third, minus 1 by root 2 for the last one. And so this is equal to root 2 by 2, which is something like 0.7. Okay? So 0.7 is bigger than half. If you compute, then the value is going to be a half plus half 0.7 is going to be roughly 0.85. So we've proven the following theorem, which is that for CHSH, this is at least something like 0.85. Because I told you how to do it. Right? And it's not that hard. You start off with this state, and depending on your question, Alice measures in the Z basis or the X basis, and Bob, depending on the question, measures on the basis that's the eigenbasis of B0 or the eigenbasis of B1. Depending which eigenvalue they get, they return that as their answer. And on expectation, they're going to succeed with probability 85%, which is bigger than 3/4. Questions on this? Is it the notation?
full expectation value can give you similar results in the four terms.
Sorry.
Yeah, okay, but there we didn't have any
Expectations?
expectations.
Yeah, so let's have expectations. So it will be the suprema. These be random variables of the expectation of something. But this is going to be always, at most, how well you can do using any given fixing of the randomness. That's where I'm using classical, right? I'm using a classical strategy, can use shared randomness, but then what does it mean? It's just a list of strategies, one possible for every shared random string. And so it's fine if you have coin flips in the background or something. I'm going to ask you, well, how well do you do on this coin flip, and that coin flip, and that coin flip, and that. So this one, this one, this one. And this calculation is showing you that in all cases, whatever it is, it's at most a half. Yeah.
There's only one copy of the state, right?
So that's a particular strategy, and that particular strategy uses only one copy of the state.
So how do you evaluate the expectation value if you can only make the measure?
Oh, no, so it's a probability, right? So I'm evaluating your success probability on expectation. So every time I play the game, you're going to either win or lose. So 0 or 1, right? But then the assumption is that I'm repeating this game many times. Each time you get to start with a fresh state, and I'm sort of computing on average how well you're doing.
Why do they make different measurements? What's the intuition?
I could set things up a bit differently, where the state would be not as symmetric, but then they would make the same measurements. There's not any particular intuition except that I'm trying to get the right correlation. And if they were making the same measurements, then it just wouldn't work out. It wouldn't be good. You can try to do a strategy where you use the same measurement, but it's just not going to be as good.
For the Bell inequality, you need to make different measurements as well. I think it kind of comes from that. Like, if you make the same measurements along the same axis, you don't get any quantum benefit. It's like correlation kind of comes in from that.
But I don't know if there's really any deep meaning there. Right? It's just try. It would be a natural thing to try doing the same thing, and it just doesn't. Yeah.
Is there an upper bound in omega strategy? Because
that's a good question, right?
Yeah.
Because what?
Because it seems like if you can reach 4, because it's not entirely obvious with 1 plus minus 1 eigenvalues as
Totally not. I agree. So that's the next thing that we want to look at. That's a really interesting question, right? I'm telling you, well, you can do 85 and using that, etc. Okay, well, let's be smarter, right? Let's just do 1. Why not do 1? So I'm going to show you why not. And this is called Tillotsen's bound. It's going to say that 0.85 is the best that you can do. That bound is going to have a lot of, aside from what you just said, it's a bound, we're going to say something more general about XOR games in general, and it's going to have, let's see, nice consequences for the theory of these games. So it's doing. And it's why is this hard, by the way? What's hard is to deal with this, right? And supremum over all states, all dimensions. How do you want that? What if they use 2 qubits? What if they use 3 qubits? Even better. So I'm going to show you a way that is going to turn out to be optimal to bound how well players can do in the game. And that way is going to rely on just one simple observation. So I'm going to start with this beta and I'm going to bound it. And the observation is going to be as follows. Is that the quantity, the more important quantity when I compute this is this, right? Is the one expectation value. So it's this, psi ai. I'm not writing the piece because the observation holds generally. I'm going to think of this as an inner product between 2 vectors. So let me write it, do this in 2 lines. So psi, and I'm going to write the middle part in this way. Because that already might not be something that's, I think we've seen it a few times, but okay. I didn't do much. I just said, well, if you multiply the tensor product of matrices by another tensor product of matrices, you get the tensor product of A tensor identity, A times identity, which is this, and identity times B, this is this. So it's just, I didn't do much. Now I'm going to rewrite this in the following way. Psi A tensor I tensor B. I'm just changing the way I'm going to go back. This is the exact same thing, except here I'm thinking of it as starting with a column vector, apply a matrix, hit on the left by a row vector. I'm saying this is the same thing. I start with a column vector and hit it by one of the matrices. Start with a row vector and hit it by one of the matrices. And then this is a row vector, this is a column vector, take the inner product. So I could write this as just, I'm going to write it this way, u times v, where u is this vector and v is this vector. What do I know about these vectors? Just one thing that I care about, which is their norm. So what's the norm of the vector v? The squared norm is equal to the inner product of itself. Okay? That inner product of itself is going to give me psi I tensor b times I tensor b. I should put daggers all over the place, but these matrices are Hermitian, so it doesn't matter. Psi. And then I times I is I, b times b is 1, so I just get psi 1 tensor 1 psi. So I just get the norm of psi. The b's just went away, and so I get 1. Okay, as long as b was an observable. So it's just a algebra manipulation, but it's an important observation, which is that in general, if A and B are observables, I can write this expectation value as an inner product between two vectors. They're defined in this way, and these vectors happen to have norm 1. This is going to have a lot of nice consequences. So.
You defined your measurements as unitary.
They're observables right now, so A and B are observables. So they squared by identity.
They're also unitary. Because their eigenvalues are plus minus 1.
That's true, they're unitary, but that's not the most relevant thing here.
No, I'm just saying, it just gives you the fact that the norm is
Well, I use that they squared to identity. Oh, because if I put the dagger 0. Yeah. Okay. Because here I'm going to do one thing here, which is write this. So I had this thing there. Let me this was just to explain where it arrived, but what we arrived at was this psi AI tensor b. Now I'm going to write an inequality here, and I write that it's less than the supremum over all dimensions d, and then vectors ui vj in CD. The norm of the vectors is 1 of the sum over ij of I, ij, c, ij, ui. Okay. The way I got there is I said, well, whatever psi and ai and bj are, I can define my u's and my v in the same way that I defined on the board here, and then I just get this expression. So I'm going to call this it's a new quantity associated to the game. It doesn't matter. Well, call it SDP of G. It's an upper bound, right? Why is it an upper bound? Because the way we got there is that we said whatever psi A and B are, I can define vectors U and V in this way that I can plug in. The big question is, did I lose? Given any vectors, is it always possible to think of them as vectors that came from observables with eigenpoints points? If yes, then there's an equality. If no, then the inequality is zero. I'm not going to show this because it's not needed. But it's a theorem by Zolzan, which is that there is equality. It's a beautiful theorem. But it says that you didn't lose. So it's a construction. It says from these vectors how to construct the state and observables such that this expression is equal to that expression. Let me make a few side comments. Why this is
this specific
actually, let me make a comment there, supply this to CHSH first. Yeah?
Just, this is for CHSH, not for.
No, this is in general.
Oh, for any.
In general, for any G XOR game. These two expressions are equal. But actually, before I make comments on this, I want to apply it, do a little practice, and so use this observation, this one-line observation, to show that the strategy that we devised for this CHSH game earlier is the best. So it is going to follow the exact same thing that we had on the board over there. So we have to remember what was going on over there. So over there, what we were trying to do is to bound the maximum bias, so advantage over random, that classical players could have in the CHSH game. And the way we did it is that we said, well, look, what's the classical strategy? It's C of bit, A0 is 0, B1. What's the bias? I just write the formula, and it's this expression here. So we're going to do the same thing in the quantum case. So the correct way to do it in the quantum case would be to say, well, in the quantum case, this is not what I have, right? In the quantum case, what I have is a state psi, and then I have the observables, A0, A1, B0, B1. And we know that if we set them to be the way I said it before, the EPR state and the X and the Z, etc., then I can do a certain value. But now what I'm interested in here is showing that it's the best that you could do, right? So I take whatever they are, and then the expression here would be wouldn't be this thing, but it would be psi A0 tensor B0 psi plus etc. until we get to minus psi A1 tensor B1 psi. Why a minus on the last coefficient? Because it's the special one, right? They will get a plus, except the last one is the special question, 1, 1, 3, and this is what we need to show. We need to show this is at most something, and we can't do it because we don't understand how large the state can be, etc. So now we have a first step here. We have kind of a little trick that says, look, whatever you can do, it's not going to be better. You can think of these as A0 applied to psi, inner product B0 applied to psi. And this is another inner product. So I can say that this supremum is going to be at most, I can forget about the state in the observables, I can just write vectors. So U0, U1, B0, B1. I think of these, right? I think of U0 as A0 tensor identity psi. I think of it in this way, but it doesn't need to be. It's just, this. And so what expression do I get here is I get U0 tensor times, the inner product, the inner product of U0 and B0, plus the inner product of U0 and B1, plus the inner product of U1 and B0, minus the inner product of U1 and B1. So that's the expression that we need to bound in the quantum case. How large can this expression be for any choice of unit vectors U and B? In the classical case, that's kind of nice analogy. In the classical case, we just had plus minus 1 values. And that's what the quantum buys us. We're not just stuck with values plus minus 1. Now we can have higher dimensional vectors that make whatever angles we like. And the question is, can you find really 4 vectors such that this is 1, 1, 1, and minus 1 times minus 1, right? 4. Then you could win the first one. Sorry.
Do we need absolute value?
It's a supremum. No. An absolute value where? Right, because they could be complex. Yeah, you're right. So I should write at least mean part.
Okay.
And in general, yeah. So thanks. You're right. I could put a there on the other side. The correct way would be just to take the mean part. Okay. And so we do the exact same thing as before. We had a proof here, so let's just continue the proof, right? So I had factorized this in this way. I can still do it, right? I mean, the inner products, they factor in the same way, except that now the inner product is U0, inner producted with V0 plus V1. And we see where there's going to be a difference. There has to be a difference because I can't get all the way there, right? That would be wrong. U1. But the first step is fine. V0 minus V1. Okay, so because this is just an equality. Now here, what did I use? I put the absolute values inside. I can do it, but now it's not products of real numbers, it's inner products of vectors. So the right inequality here is the Cauchy-Schwarz inequality. So I'm just going to say something simple, which is that the inner product of 2 vectors is at most the product of their norms. Right? That's the Schwarz inequality. And because the u vectors have norm 1, I can write it like this as a quarter times, and then I get the norm of v0 plus v1. I'm not writing the kets, but this is just a sum of vectors, plus the norm of v0 minus v1. Okay. Here's where you have a difference, right? When these were plus minus 1 numbers, we said, well, there's not so many options. Either this is 2 and this is 0, or this is 0 and this is 2. So at most, the whole thing is 2 divided by 4. In the case of vectors, it's no longer true. And the best that I can, the best that I can do is, I write it in this way, so it'll be less than the supremum of a quarter. I use again, I don't know how it's called, like arithmetic geometric mean or something. So I say that this is less than square root 2 times square root of the sum of the squared norms. Okay. And then now I'm done, because this is equal to what? It's equal to a quarter times square root 2, so square root 2 divided by 4. And now I can expand my squares, right? And I'm going to get the norm squared of v0, that's 1. The norm squared of v1, that's 1, plus the cross term. Here I get the norm squared of v0, 1, norm squared of v1, 1, minus the cross terms. Cross terms cancel out, so I just get 4. So I get square root 4, so which is square root 4. And so square root 4 is 2, so I get square root 2 over 2, so I get 1 by root 2. So that's what we had called an earlier. So that's the proof that the strategy that we found for CHSH earlier is the best strategy. And the proof uses two things. First, it uses that we can bound the expectation, we can write the expectation value of the quantum strategies as this inner product of vectors. And then we can do a linear algebra on the vectors to get to that. Questions on that? That proof has a nice feature that is going to be relevant a little bit later when I talk about these rigidity properties. Is that not only does this bound hold, but let's try to achieve it. What do I need of my vectors in order to achieve this optimum value of 1 by root 2? And the point is that I don't have so many options, because in order to get here, for this expression to be equal to this expression, the vectors need to be aligned. To get equality here, I need to have u0 equal to v0 plus v1, or proportional to v0 plus v1, and u1 to be proportional to v0 minus v1. If they're not aligned, then I wouldn't get equality here. The second inequality is that inequality, the Cauchy-Schwarz inequality here. And this would be an equality if and only if these two terms are equal. And so for these two terms, or not to get, which is the same as saying that I don't get the cross terms here, so to get equality here, I need the vectors to be orthogonal. V0 orthogonal to V1. So I don't have a choice. The only way to find vectors that have a value 1 by root 2 here is that V0 and V1 should be orthogonal vectors. And u0 and u1 should be related to v0 and v1 in this way. V0 plus v1 by root 2 and v0 minus v1.
So this works if AI and v0 are all just arbitrary.
Sorry? Yeah. Arbitrary observables.
It could be also just any unit.
Yeah, that's true, but the game is such that in the game you give plus and minus 1 answers. That's the specification. Or if you say something that's not plus 1 and minus 1, I'm just going to reject it. So they're unitaries with plus minus 1 eigenvalues. But yeah, you're right. I wanted to make a few comments about this equality there at the bottom. So it has some interesting complexity theoretic consequences, and because someone asked about complexity theory earlier, So I'm not going to fully justify this, but there's a reason why I call this SDP. So for those of you who are familiar with linear programs and even more semi-definite programs, that's kind of a generalization of linear programming, this expression here, this supremum, you can express it as a semi-definite program. Basically because it's an optimization over unit vectors, and the linear function, the objective function, sorry, only involves inner products of these vectors. So if you haven't seen SDPs and you can't understand what I'm saying, but if you've seen that, you could see that this is a semi-definite program. Now, there's something important about SDPs, that just like NPs, you can solve them efficiently. Which means that this supremum, given the description of the game, is something I can compute. There's an algorithm, I can run it on my classical computer. And I can determine what is this supremum. And because of this theorem, this supremum is the best that the quantum guys can do. So the consequence of what we've said, given, and this is a bit surprising maybe, but given XOR game, just a description of the game, it's hard to determine the best strategy that the classical players can have. There's reduction from max cut, for example. But it's easy, at least polynomial time, to determine what is the best that the quantum players can. You can solve this SDP, you can find the optimum vectors, you can apply Zellson's theorem, you'll find a strategy. You know that this is the optimum, and the proof of the theorem is explicit. It takes the vectors and it gives you a strategy for the players.
In quantum case, we have to calculate SDP for all B.
But that is true, but okay, so here's another interesting point, right? So, thank you. So this was how well the quantum guys can do, right? And we said, well, what's the dimension? I don't know, they can use as high state as they want, right? And so here, for the vectors, the way I have defined the vectors, they can be of any dimension, right? So I have to take a supremum over 2. Okay. What does the objective value depend on? The inner products of the vectors. So suppose I have n vectors u and m vectors v, and they're in a super large dimension, but the only thing that I look at is the inner product between these vectors. And I claim that I didn't need such a large dimension, because if the only thing I look at are the inner products of the u's on the v's. So I can project them on the span of the v's. And the v's I can project on the spans of the u's. And so in fact, just once I rewrote this, the next line I could have written equals, but I don't need the d, I don't need this. The only thing I need here is the minimum of the number of questions to Alice and the number of questions to Bob. And so then it becomes bounded, and there's just a single SDP, and you can solve it efficiently. This possibly infinite dimension completely disappears. That's something that's very special about XOR games. Due to these results, we know that these XOR games, you can always play them optimally using a certain amount of entanglement that's bounded as a function. That's not true in general. If you look at more general games,
is that part of the theorem?
Which one?
The fact that D equals min.
No, it's that's just an observation. So which is that if I write the supremum over vectors of any dimension, because the inner product, it only depends on the inner product, I don't need them to be a very large dimension.
Okay.
I can just project them down to the span of the objects. What the theorem, what's part of the theorem is that if you solve this and you get vectors that achieve the optimum that have a certain dimension, I can find a strategy that uses as many qubits as the dimensions of the vectors. That's part of the theorem we're not going to do.
Yeah. For general games, if you limit the amount of dimension, can you bound the quantum value in terms of the classical value?
That's a good question. Yeah, there's partial results in that direction. So it can always be, the quantum value can be at most a multiplicative factor times the classical value, and that multiplicative factor depends on the entanglement. So in fact, for those of you who do functional analysis here, another consequence of that theorem is that you can prove the following. You can prove that so the quantum bias can be larger than the classical bias by how much? At most a constant factor. What's that constant? It's called a Lee constant. It's something that comes from functional analysis. It's like 1.7 or something. And so it bounds this. And that's sort of black box application for the Gleason inequality, but I am not going to explain it. So for XOR games, the quantum pairs can with most of the constant factor times the classical pairs. This is another. Okay, so maybe I don't know if, so we still have half an hour, but do we want to leave like 4 or 5 minute break, bathroom break maybe? So what do we need to do in the remaining 25 minutes? So what have we done, right? So I introduced a model of XOR games, and that the prime example of that class of games was the CHSH game. And we studied how well the classical, or what's the classical strategy, what's the quantum strategy, and then we asked the question, how much better can quantum strategies do? And that question is related with how do we bound how well quantum strategies do, and that led us to Tilderson's bound. And we proved that, right? And so now we know that for the CHSH game, we know what a strategy is for the quantum pairs, and we also showed on that board that that strategy was the best that you could do. Now in the meantime, what I want to go a little bit further and tell you how this game and the properties of this game can be useful in order to achieve, for example, delegation. So that's the rigidity property. I want to just sketch the arguments that go into showing that the strategy that we saw, the X, Z, Hadamard, whatever, for the CHSH game is the best that can be achieved. Is the only one that achieves the optimal value. And that's going to be useful because it lets me use the CHSH game as a test for the fact that quantum pairs or provers apply certain observables on a certain state. I just play the CHSH game, and if they do well, then I know what's going on. I know these guys have an EPR pair, I know Alice has been measuring either in X or Z, and I know Bob has been measuring either in Hadamard or this other operation that we have. Once I know that, I kind of have a handle on what these guys are doing. I know it. I know they have an EPR state, I know they make X and Z, and then it's possible to bootstrap this all the way into checking that these guys are implementing a full computation. Not only just X and Z, but whatever, right? C naught, other gates, you can check that. So that I'm not going to show you, but you can do it based on simulation. What I just wanted to show you is the kind of argument that go into just showing this, showing that the strategy that I gave you for CHSH is the ultimate strategy. Yeah.
So how can you actually test an X when you do a change of basis?
Yeah.
Then it doesn't do it to as a vector set, right?
Yeah. So it's just like here, the characterization that I got was that these vectors are orthogonal, but there's many orthogonal vectors up to rotation, right? So the characterization would be exactly this. It would be that it's exactly this strategy up to a local conjugation by rotation on Alice's side and conjugation by rotation on Bob's side. But these rotations have no observable consequences, so whenever I talk about a protocol that just has classical things coming back and forth, it's not going to matter that there's a degree of freedom. But you're right, that's a degree of freedom. Well,
so do you want the 5 minute break? Thomas, what do you want? You want the 5 minute break maybe?
Yeah, there's two ways to do it. I was thinking because no one's moving, so I don't know. I think maybe a break is needed, but I can also do this. Okay, so break is needed. Okay, let's take a 5 minute, not too long because I don't want to run over the clock, but then I'll, it'll be 20 extra minutes after the break. So let's take a break.